All right, we'll see if my computer's actually working now. I think we're good. Can see it, things are working. Okay. All right, good morning, everybody. We have an exam coming up on Tuesday, so we'll spend, I guess, the first little bit just opening it up to you and see if there are any questions on the exam material or any general questions on the exam. And I feel like in a good spot, we know how things are going to work and what's on it. Yeah, Ryan?
So, for like a lot of homework problems, they have like geometry-specific equations. How is that going to work? Are we just expected to know like around a cylinder, over a flat plate, like?
Yeah, so that's a good question. So the question was on geometry-specific equations, especially, I'm assuming in regard to convection.
Yeah.
So with regard to convection, we're only going to be covering on the exam up through external convection. So it's only flow over top of an object. We'll talk today about a little bit more about internal, like flow inside of something. And we'll start on free convection. That's not on the exam. The only convection stuff that will be on the exam, you will be given, so trying to remember what equations I gave. I think I just gave a couple on the handout. Is that right for the one posted on Moodle? But I guess the short answer is there aren't going to be a whole lot of possible geometries that I'll ask about. But if you look at okay, so if you look at the unit conversions, equations, tables, so some of the same tables here as what we used for the quiz that we had a little bit ago, which may or may not come up. Same there. So those are the only equations that I'm giving you for convection. So those are the only correlations that you will need for convection. So I won't ask you about shapes or systems that are not covered by those ones. And I guess, by the way, you're welcome to, if you want to like kind of take notes about what's, like, as you're looking through this, I would say look through this, and that may give you some idea of what is possible. Yeah, so I'm not expecting you to write down every equation that's in the book. These are the different ones that you might end up using. So yeah, thank you. Good question. Anything else? Yeah, Rachel?
Can we like print this off beforehand and take notes like we did for like the one quiz, or would you rather like a separate note sheet from this?
So yeah, what notes are allowed? So the question was, can you print this off and just take notes on this? I'm fine with that if you want to do that. Yeah, I'm fine with that. Yeah, I guess if you are going to do that, just send me an email so I'm not printing off 20 copies of these and nobody needs them. We'll save trees. But yeah, you're welcome to do that. That's fine. Okay, anything else on the exam format or questions or topics? Okay, hopefully it's fairly straightforward. Transient stuff, some basic convection stuff. I guess, so maybe elaborate a little bit on Ryan's point. Like if I gave you, I could give you a different type of shape and ask you something about the convection, but it would be in a little bit different context. Like if I gave you a model for H and asked you to find it, So I would either, it's one of those models that I just showed, or it's something that I'll specifically give you and say, this is what it looks like. Or it could be a problem like a similarity problem where you're not really looking for that same type of correlation. You're just trying to compare system A to system B. Okay, is that, I don't know, hopefully you guys feel ready for the exam. I'm going to release the solutions to this week's homework after class today. So if you want to look at those for study help, it's a good spot to look to. Okay, and hopefully this example problem that we've kind of been working through last time and today will be some review of how to think about some of these things as well. Although obviously much more pieces, many more pieces than you would find in an exam question. Okay, so when we talked about, right, remember what we're trying to do. We're trying to figure out temperature of the water in this pipe as it's flowing underground and how that temperature is changing over time. So we have a couple different pieces of the model that we're trying to build. The first thing that we were looking at and where we sort of ended last time, if I'm remembering right, we ended saying, okay, how are we going to find convection? Well, we're going to need a Reynolds number and a Prandtl number. But we said for this kind of a system, that's not totally enough, because just a Reynolds number and a Prandtl number doesn't take into account anything about like how long the pipe is. Because in an internal flow system, Reynolds number has the diameter part, but it doesn't have any information about the length part. So we'll need something else to do with length. That's where we talked briefly about what we call the thermal entrance region, which is a way that we can kind of characterize length of a pipe. So we can look at, you know, how long does it take in this system, in this geometry, in this size, for heat to move from the walls into the center of the flow. It's a kind of a reasonable parameter to start to kind of build lengths around. So are we twice that? Are we half that? Are we 100 times bigger than that? Where do we stand in relation to that? And that's going to be key in getting us what our, that's kind of our length information that we care about. That's going to be non-dimensional because it takes into account kind of all of the key parameters, but it's going to help us kind of normalize any length in the system based on that. So again, saying like we're twice as big as that, we're 10 times as big as that, we're a quarter that size. Gives us an idea of where we stand in terms of the length. Okay. So we did a lot of this last time, so I'm not going to go over all of it, but this gave us a correlation for, and I think this is what we ended on last time. Stop me if I'm skipping ahead. I believe this is right. Correlation for our average new salt number, which was 3.66 plus 0.0668 times the Gratz number, which is right this non-dimensional length, divided by 1 plus 0.04 times the Gratz to the 2/3 power. We ended on this part, right? And seeing head nods. Good. So this is how we're going to find, and this is the general way we're going to find new salt numbers. We're going to say kind of what are the key parameters, and then let's take these key non-dimensional groups and use those to build a correlation for the Nusselt number, which is our non-dimensional heat transfer. And then we can find H because, right, the Nusselt number is going to be H D over the thermal conductivity of the fluid. Okay, so this gives us a way to look at Nusselt number, which gives us a way to look at H. H is the Nusselt times the thermal conductivity of the fluid divided by the diameter. Okay, so that's the way that we can attack the convection coefficient, but that's just a piece of our larger problem. So the second step that you guys worked on was determine a model to describe how heat flows from the soil into the fluid. So there we were looking at a cross section of the pipe where we have like water inside of the pipe, right? It's flowing out, and we have this pipe here. This is PVC. The dimensions here are 12.5 millimeters. This thickness is, I believe, 8 millimeters. And in this case, we know that the surface is 10 degrees C. And basically what we're saying there is the PVC pipe has relatively low thermal conductivity. The soil has relatively high thermal conductivity. So it's going to be pretty easy for heat to get up to move through the soil, but it's going to be slow for heat to move through the pipe. So it's reasonable to say that outside of the pipe is probably a constant temperature, because that's probably the slow point. So if we're looking from heat flowing from the outside, right, we have heat flowing from the outside into the inside. We're looking at kind of at every point along the system. It's going to look like this. We're just looking at a single slice. And we can say at this point, we can think about this as a thermal resistance problem, right? Heat first has to go through the pipe, and then it has to go into the fluid by convection. So our thermal resistance model is the equivalent resistance is R PVC plus R convection. And because our pipe is relatively long, and this is just a single section, we're going to get heat transfer. We're going to get resistances per unit length. So this is equal to, well, our PVC is the natural log of R2 over R1 divided by 2 pi K. If you just look up the equation, it's 2 pi KL, but we're kind of taking L out of the equation. And then for our convection is 1 over H bar times P, where that's the so these are both per unit length. So another way to think about that is we could have chosen like a length unit of 1 meter, and then these would have been the per meter values. That's exactly what we did, is we chose, like, this is the same as saying we have this is for a 1 meter length. And then we'll use that to kind of scale up to the final length. Okay, so we have an idea of what's happening inside the pipe with convection. We have an idea of how heat moves from the soil into the pipe, or into the fluid, into the water. And then the last step is to figure out how the fluid's going to heat up as it travels. And this part is a little bit harder to just come up with, I think, than the other ones. But if we think about it, it's coming in, the fluid's coming into the system at 0 degrees. It's going to be heating up. We have the biggest temperature differences initially. And when it comes out, obviously, we're going to have small temperature differences. It's going to look something like this. So this is our X position, which is our length along the pipe. This is T. So if this is 10 degrees C, that's our soil temperature, and this is 0 degrees C, we would expect it to look something like that, right? It's going to start at 0 and then be approaching 10 degrees. If we think about, again, what we can look at in terms of the fluid temperature, it's going to be a little bit messy because we're going to be coming in here. Probably all of the fluid is pretty much going to be 0 C. So we're coming in at a relatively constant temperature. But if we look at, say, this point here, we're no longer at constant temperature. The fluid by the walls is hot. The fluid in the center is still 0 degrees. So it makes more sense for us, because we don't particularly care in a system like this what the temperature is at any given location in the pipe. We care about the average temperature at that pipe or at that location. So we can kind of approximate this and say, well, the temperature really isn't, we don't care that it's different in different places. We can just pretend that it's some constant average temperature. So we can look at average temperature, because that's, again, when we're talking about it coming in at 0 degrees and leaving at 8 degrees, what we're really talking about is we want the average temperature leaving to be 8 degrees. Because then we're going to do other stuff and maybe it's all going to get mixed together and turn out 8 degrees. That's what we want. We don't care if the center is 7.5 and, you know, a little ways away from the center is 9, as long as the average is 8. Right. So we're going to kind of approximate these temperature distributions at every point as just a flat average, and kind of neglect the fact that there are actually temperature distributions there. We're not totally wiping away all of the temperature distributions, because those temperature distributions are what give us H. We're just kind of in terms of how we're looking at it heating up, that's how where we're neglecting those temperature differences. So this is that's the average fluid temp. So this is going to behave somewhat like right, we showed we showed this example, or I showed this example from a super long time ago. It's going to behave a little bit like this. So in this example, we had cereal starting at one temperature and coming out at a final temperature. As it moved through the system, heat was flowing into the cereal by convection. In our case, we have heat flowing through like a multi-step process, but same thing. Heat's flowing into the cereal by convection, and that's causing the amount of heat in the cereal to increase as we go along the conveyor belt. So as we're moving from one side to the other, our temp is going to do the same kind of thing. We said that this was, we kind of, again, in this case, neglected temperature differences in the cereal. We could do that because temperature differences were super small. They're not as small in the case that we're looking at right now, but we're still going to kind of, to a first pass calculation, we'll still neglect those. So we had how long is the cereal in the oven? Well, that's going to have to do with the velocity that it's moving through the oven and how big the oven is. So the same thing, we're going to have a time variable that's related to velocity and how big our pipe, how long our pipe is. That's how long the residence time for our fluid is. Okay, so if we look at that model, the lumped capacitance model, is theta over theta star minus T over R over the equivalent resistance and the thermal capacitance. So now we just have to figure out what those pieces are, right? This is the problem. These are the things that look just like a capacitor discharging across a resistor. You get the same RC time constant. We just have to figure out what R is and what C is. R is the easy one. It's what we found before. So R is right there. So we just have to take that and plug it in down there. So we take that equivalent resistance that we calculated in step 2. The capacitance and the time are a little bit different. And theta over theta star is a little bit different. So theta over theta star in the lumped capacitance model is T infinity minus Ti over, or sorry, T infinity minus T over T infinity minus Ti. Right, so what we're trying to look at with the theta over theta star is like the percent of the way that we've, again, if we think of this picture up here, we're looking at, like, as we move along, the percent of the way, like that percent, the percent of the way between the two temperatures that we've reached. So this is going to be, so T infinity is going to be our temperature far away. That's 10 degrees. So this is going to be T soil. Our temperature, say here, we'll call that, that's like T2 average. The average temperature at the outlet, or wherever that happens to be. And then here we're again T soil minus T1 average, which is 0 degrees. Okay. minus T over R so this one the time component is like the residence time length over I don't know quite what variable to use. I'll just write it. The length over the velocity. R is R, that's a straightforward one. The thermal capacitance is how much heat a unit of mass of this material is able to hold, how much heat this material is able to hold. So this is rho V CP, where V, right, that's the volume. And if we take these three things and kind of we're combining all of them, minus T over R this is going to be minus L over R well, so this guy, we're going to look at it, grow times area times CP, not rho time. So again, because our fluid is flowing through the system, so we'll combine. Let me move some of this over. Okay. So minus L. I'm going to use U for velocity so that I don't have to write it out all the time, but hopefully that reminds us that's what that is. So this is R minus L over U rho A CP, which is equal to minus L over R times the mass flow rate times the heat capacity. Okay, so now our challenge to actually solve this is to now start taking things and moving them from the equation stage into some sort of thing to actually solve. So to solve this, we need a defined length because all of our different parameters depend on length. So what I'm going to do is throw this in Excel, and we'll be able to see a little bit how to solve that, if that works. Okay, so I set up a spreadsheet where we can see at least some of the variables and such. So our our heat capacity was 4206. Our viscosity is 1560 times 10 to the minus 6 Newton second per meter squared. Thermal conductivity is 0.577. And our density is 1,000 kilograms per meter cubed. What else are we given? So we're given an initial temperature of 0. We're given the ground temperature or the soil temp of 10 degrees C. Diameter is 25, or what is the mass flow rate here was 0.05, is that right? The diameter is 0.025. Okay, so the pipe, the thermal conductivity is 0.47 watts per meter cubed, and the thickness is 8 millimeters. So that's 8 e to the minus 3. Anything else that we're given? So we're given a Prandtl number as well, 11.44. Okay. So I think that's all the givens. So then we can calculate some basic things. We have an unknown length, but for getting basic numbers, we have to just choose one, and then we'll be able to vary it at the end. So let's choose a length. Does anybody have a favorite length? Pick a length. How many meters?
22.
22 meters. Okay. So we'll see if that's right. Does anybody have a guess? Like, is that a guess of how long it should be? Okay. It's gonna be perfect. Okay, so area here. So area is I times d squared over 4. So that's meters squared. Our velocity is mass flow rate divided by area. What is it going to be? It's mass flow rate divided by area divided by times density. Get my parentheses right. Area times density. 0.1, that's meters per second. What else do we have? So then we can calculate Reynolds numbers and Gratz numbers and figure out those. So the Reynolds number is rho, velocity, diameter divided by viscosity. 1,630-ish. Right, so that means it's laminar. Is good. That's what we had, I think, calculated before. The Gratz number is equal to diameter divided by length times Reynolds number times Prandtl number. Our Nusselt number, we had a maybe. Okay. We had a correlation. So this is our correlation for the Nusselt number. So we'll throw that in 3.66 plus whatever for the Gratz number. So this is equal to 3.66 plus 0.0668 times the Gratz number divided by, what is it? 1 plus 0.04 times the Gratz number raised to the 2/3 power. And we'll see if I got my Okay, so that gives us, let's get just a normal number for all these. Okay. All right. So our Reynolds number is 1630. The Gratz number is 21.2, and our Nusselt number is 4.7. And hopefully, if we change the length, if length is shorter, our Nusselt number should be bigger because we have more heat transfer at the start. Okay, so that works. So this is 22. If we go to like 100, then it gets smaller. All right, what else? So then our next step is to do the stuff that figure out a value for H, like what we're doing right here, and then put this, the thermal resistance stuff, put this thermal resistance stuff in. Okay, so our H value is the Nusselt number times K divided by diameter. So our H value is 109. And then thermal resistance is, so for convection, it's 1 over H times the perimeter, which is 2 pi r, or pi times the diameter. So that's times pi times diameter. So that's our resistance for convection. The resistance for the PDC is the natural log of R2 over R1. So this is the D divided by 2 plus thickness. Put that in parentheses. That's R2 divided by R1 divided by, wait, what was it? Divided by 2 pi K. 2 times pi times, okay. All right, so we can see here we actually have the thermal resistances are on the same order, like about 0.1-ish. So we couldn't have said like heat transfer is slowed by both of those things on kind of the same scale. Our total, because these are in series, it's just the addition. And then we have to find T2. So T2, we're going to be essentially using this model here, solving for T2 average. So it's going to be, let's see if we can get this right. So this is equal to no, T, let me just write it because otherwise I'm going to screw up signs. So this is T2 average is equal to T soil minus T1 times the exponential of minus L over R m dot CP. But then we had to rearrange that guy, so that's so this would be I guess T-soil plus that. I believe that's the right sign, I think. Okay. So this is going to be equal to T-soil plus the temperature difference, which is T-soil minus T1. T-soil minus T1 times the exponential of negative L divided by R times the mass flow rate times the heat capacity. Did something wrong.
I think it should be subtracting instead of adding.
I think you're right. So let's see. So 3 degrees maybe makes sense. It's at least between 0 and 10. So if we made this 10 meters, then it's 1.65. If we made it 1,000,000 meters, 10 degrees. So that looks like it's working right. Okay. So what we can see here, now we have a model that we can play with and start to change things around and figure out how different parameters are going to actually influence the system. So for example, we can solve this and find how long the pipe needs to be. So we could use something like solver. We want to set this, we want it to be 8 degrees. So set it to a value of 8 by changing the length. And if we solve that, we see our length there is 104 meters. Right, so those are kind of our two critical things. We could also look at, like, right, if we're getting, as we look at the thermal resistance, we're getting about half of the resistance to heat transfer just because the pipe has really low thermal conductivity. So if we said, what would happen if we changed the pipe to some different material that had a thermal conductivity of, say, I don't know, even like 3 times that. So say it was like 1.5. How much can we cut down our length? So let's just redo that solver problem. We could cut down the length almost in half by bumping up the thermal conductivity a little bit. So that might be something, maybe it's more expensive to make a little bit higher thermal conductivity, but if we can cut down the length in almost half, maybe that ends up being worth it because you have less drilling and stuff to do and you use less pipe. So you can start to ask some questions like that. We can look at how changes in flow rate. So if we went from, say, 0.5 to 0.025, we see when we have lower flow rate, our velocities are going to go down. So it's going to be in the pipe for longer. So we can see with the same length, we now have a temperature of almost 10 degrees. So it's really sensitive to flow rate and how fast we're moving through this pipe. You can see that here. I plotted up some stuff, again, just to kind of get a feel for how, in this case, how one variable is going to be affecting our temperature. So this is pipe length on the bottom. It's kind of hard to see that. I should have made my font bigger. I don't know. I'm not going to do it now, but pipe length on the bottom and temperature on the Y. So temperature, obviously, the top is where they kind of plateau is 10 degrees. So you can see these are 3 different flow rates: 0.1, 0.01, 0.03, and 0.05 kilograms per second over 100 meters. So you can see how sensitive, say, the outlet temperature is to flow rate and get a sense for how we can use this model to understand the design of what our final system is going to be. So building even simple models like this can help gain intuition as to like how we should think about this and what factors we should focus on when we're designing it, and maybe what factors we can change and improve heat transfer or reduce costs of our system by reducing, how much pipe we have to actually put underground, things like that. And then, okay, we could imagine this is one aspect of a broader system. You guys in heat transfer class looked at some aspects of the heat pump part of the problem. So we could take now what's happening in this and start to apply it to the heat pump. And maybe, okay, the heat pump has another heat exchanger, so we could start to model how big does that heat exchanger have to be, and what components and what pipes and what are the thermal conductivities, and build models for other aspects of it. Maybe the heat exchanger for the heat pump has fins on it to improve heat transfer. So you can see we would kind of take different aspects of the system. We want to break it up into as many pieces as we can, build individual components of that, and that can help us gain intuition on the system as a whole. Okay. So the last form of conduction that we haven't talked about, convection, that we haven't talked about yet, and we will just talk about quite briefly, is free convection. So we won't spend tons of time on this because I think you kind of get the idea of how mathematically we treat convection problems. You figure out what are the important dimensionless groups for this geometry or for this system, and then figure out correlations between those non-dimensional groups and what's happening with the heat transfer. See if this comes. But I do want to spend a little bit of time on the physics of free convection, because I think that helps us to think about problems and how the physics of problems influences models that we're going to build of those problems, which is, I guess, like outside of the context of heat transfer, some of the broader things that I think are take-home messages from the class is how do we take the basic physics of what's going on and use that to inform correlations and models that we can build to describe things. So if we look at, this is jumping up to chapter 9, if you want to look at this in our book. This is free convection. So free convection, this is where we still have fluid flow, but it's governed by density gradients or density differences. Caused by temperature gradients. Right, so hot air rises. So when you have hot surfaces, there's going to be fluid flow that's governed and driven by those density differences, which are caused by the heat differences. That's true for both liquids and gases. So if we think about, again, if we had, like this is T cold, This is T hot. So I'm assuming gravity is pointing down. So geometry and where gravity is has a huge effect on this. But okay, so what would happen in this case? Well, you would get the hot air by that bottom plate would tend to want to rise. And the cold air at the top plate would come to fill its spot. And you would get a circulation in that channel. So this would be an unstable fluid circulation. You don't get that in every case. So you can get it where maybe the gap is really small or the temperature difference is not that big. And you can have a system like this where, you know, kind of the setting is just right, that viscosity in the fluid keeps everything still and keeps it from moving. That can happen. We'll look a little bit later at when that would happen, when you wouldn't get this recirculation. If instead of that, if you had a very similar case, but you had something like this, but right, our hot plate is on the top and our cold plate is on the bottom, then there is no tendency. The hot air is going to want to rise, but the hot air is at the top. The cold air is going to go down, but the cold air is already at the bottom. So you would have, in this case, you'd have a stable fluid layer. There wouldn't be this recirculation, and you would have heat transfer just by conduction and radiation potentially. So the challenge of free convection is that geometry matters a ton, and exactly what the system is, like how the system is sitting and where hot air is going to go and where cold air is going to go, plays a big role in like kind of the details of the physics. We're not going to spend too much time on it, other than to cover some of, again, kind of the high points of it and take note of some of the geometry considerations. So so our flow in this case is driven by buoyant forces. Right, so it's driven by differences, relative differences in density, or relative differences in the weight of the fluid. So it's driven by buoyant forces. We can look at again, just maybe a couple different pictures of what like the physics would look like if you had. So another example. If you had a hot wire, or like this could be either a two-dimensional, like in and out of the page hot thing, or it could be like a kind of a point heat source, like a candle. In that case, what would happen, right? You have your fluid flow is going to kind of be up like that. There's going to be a line of symmetry in the middle, and you have that's a bad. So you have a velocity that ends up looking something like this. And you're kind of constantly taking air and really sucking it into the sides. So in this plume, if you want to call it that, you have, again, really kind of a lot of things going on. So this is where density is less than what I'll call density infinity. So this is where your density has changed, and that's what's causing that section of fluid to rise. So this is T greater than T infinity. Where we'll start kind of actually digging into what the math looks like, or what models look like, is a vertical plane wall. So we're imagining in this case, so this vertical wall of some constant temperature Ts. What's going to happen is somewhat similar to what happened when fluid was like forced to flow along a flat plate. You're going to get a boundary layer that grows along the plate. The difference is kind of what the velocity looks like, where when we were forcing flow along a plate, it was like the free stream velocity, the velocity far away was, say, 25 meters per second. The velocity at the surface was 0. When we're just allowing natural convection to take place, the velocity far away is 0. So our velocity profile looks a little bit different. So it starts and then kind of comes back to 0. So this is the velocity u. But the thickness of that is going to increase as you go up the plate for kind of the same reasons that the thickness increased for flow along a plate. So it's a lot of the same kind of physics. So here we have, this is vertical, so G is down. So this would be the velocity part of the system. There's the velocity part of the system and the temperature part of the system. So we'll redraw the same system, the same wall. So this is so the temp part of the system, we're going to have a similar boundary layer growth. Let's imagine, right, this is a hot plate and a cold fluid. Similar boundary layer growth. Our surface of the fluid is going to be at Ts, and it's going to cool off to T infinity. Like that. Um, so what's governing our flow in this case, right, is buoyancy. And buoyant forces, it's because the hot fluid is rising. So our flow is driven by this thermal expansion. So you can maybe see from the temperature boundary layer at the right, we're going to have maybe a little bit more complicated dynamics than we do for something where we don't have density gradients really playing a role, because we have differing forces right near the wall. We have a lot of buoyant forces because the density is going to be low because that's where we're hottest. Far away from the wall, we have less of that. So we have to take kind of this added. We can't just take into account like Reynolds number and Prandtl number. We're going to have some added complication related to what's happening to density. So for this, our flow is driven by density gradients or thermal expansion. So it might be reasonable to expect like there's going to have to be some non-dimensional thing related to thermal expansion and density and stuff like that. Okay, so we'll first start by kind of characterizing how thermal expansion works. So just like a fluid has a property of like thermal conductivity, you can describe a fluid, how it expands with temperature. What's the thermal expansion? So that's the first part that we have to define. Is define / characterize because if two fluids, like say one is a gas and its thermal expansion is ideal gas law, and one is a liquid and its thermal expansion is totally different, those two things are going to behave completely different. So we have to be able to characterize that. So we do that with the volumetric thermal expansion coefficient, which we'll call beta. So the way we define beta is -1 over density dt at constant pressure. Let me explain what this equation is. Well, we're not going to actually be using that to calculate things, but that's what beta is. So this is talking about the change in density with temperature at constant pressure. So again, going back up to like this flow on the vertical plate, that makes sense that that's what we would care about. We're caring about how density changes with temperature, not how density is changing with pressure, because pressure is constant everywhere in a lot of these cases. But then we're also like throwing in this guy. So we're normalizing to what the density is. So you can think about it, it's kind of like a % change in the density with temperature. So it's a normalized change. For an ideal gas, we can actually just calculate this. We can calculate this fairly easily. Right, we would say P times 1 over density is R times temperature. Or that the density is equal to the pressure over RT. So we can calculate from ideal gas law, d density dt at constant pressure is the temperature derivative of P over RT. Right, just a reminder, this means at constant pressure. So it means pressures we can treat as a constant. So that means pressure and R are both constants, so we can pull both of them out of the integral. So we have pull both of them out of the derivative. Pressure over R times the temperature derivative of 1 over T. Just simply P over R negative 1 over temperature squared. Right. Then we can calculate our beta is negative 1 over rho d rho dt at constant pressure. So this is negative 1 over rho is RT over P. And d rho dt is P over R minus 1 over T squared. So now lots of things are going to cancel out. Lots of things cancel out. So we have a P there, which cancels out with the P there. That negative will cancel out with that negative. This R will cancel out with that R. And that T will cancel out with one of the T's on the bottom. So we get, for an ideal gas, beta is 1 over temperature. Right, because pressure and volume and temperature are all related like that. So maybe it's not too surprising. That's how thermal expansion works for ideal gases. For a non-ideal gas, for a liquid, we can look up beta. So our book has some of this in some of the tables in Appendix A, or you can measure it fairly easily. You can look at different temperatures and measure how the density changes. Density is pretty straightforward to be able to measure. So you can look it up, you can measure it. In general, it's going to be a strong function of temperature and a relatively weak function of pressure. So on T, especially for gases, it doesn't change as much, nearly as much for liquids. And it's generally a weak function of pressure. Again, for ideal gas, that's kind of, for gases, that's a good place to look back to. It depends on 1 over temperature. So it depends really strongly on temperature. Pressure doesn't even show up. So for a non-ideal gas, it's going to be kind of the same thing. Pressure is going to, okay, pressure does show up for a non-ideal gas, but only a little bit. Temperature still shows up a lot. That's going to characterize, if we go, again, we're going to kind of take some of this, and for all of these things, we're going to go back to the physics of what's happening to try to understand what are the important groups of variables, what are the important things that describe the physics, and then use those groups of things to be able to make our correlations. So if we look back to the physics of what's happening, the velocity is going to be dictated by the momentum equation, by the Navier-Stokes equations. The temperature is going to be dictated by the energy balance. That part really doesn't change. What changes is that what's driving flow in the momentum equation is buoyant forces. So that's the part that's going to change a little bit, or that's the part that we have to take into account that we haven't done so yet. So the momentum equation is U du dx plus V du dy minus 1 over the density dp infinity dx minus G plus density divided by mu d squared u d y squared. Okay, so for this, we have to ask, what are the important parameters if flow is governed by these temperature induced density variations and gravity. So that's the question that we're going to ask. We have kind of the whole picture of the physics. We ask what's important if this situation is true, if we're really governing the flow by density variations and gravity. So we'll look at that. We'll look at, we're not going to go into a lot of detail, but we'll look at kind of what falls out of that next time. And that will be on Thursday because we have our test coming up on Tuesday. So feel free to reach out to me if you have questions on the test or if you want help going over stuff. I'm happy to help out. Otherwise, I'll plan on seeing you all on Tuesday. Yeah. Have a good weekend and good luck studying. Thank you.
I'm gonna need it.